Hello. Today's video is for Physics 151 students getting ready for the 9th week of practicals. It's all about Chapter 10 from Wolfson's textbook on rotational motion. I hope this helps your practicals go a little more smoothly.
Okay, so we start with angular position. So if we have some circular path, an object or a little particle on a circular path of radius r, we can keep track of its position either with the distance it travels, s, which is arc length, or with the angle that it makes with the center of the circle, theta. And if you go all the way around, then s is 2 pi r. The angle can be specified in radians, so that it's 2 pi radians to go right in a full circle. In that case, we have a nice equation to give theta in terms of s, the distance traveled, divided by r, the radius of the circle. So it's good to use radians. And keep in mind that 1 radian is 360 degrees divided by 2 pi, or about 57.3 degrees. This is about a radian right there. So now we talk about angular velocity. This arm rotates some angle delta theta in a time delta t. So its average angular velocity, we call it omega, with a little bar on top to mean average, is delta theta divided by delta t. And the direction for positive angular velocity is usually counterclockwise, because we usually start from the x-axis and go up towards the y-axis. And then similarly to how we did with regular velocity, the instantaneous angular velocity omega is the limit of the average angular velocity in the limit that delta t goes to 0. So that's the same as the derivative d theta by dt. And it turns out that the linear velocity v that we're of particles on a rotating object is related to omega times r. So what that means is that as things get further away from the axis, they're all traveling at the same angular velocity omega, but the linear velocity v goes up proportionally to r. It's going slowest, actually 0 right at the axis, and then fastest right out at the rim. Next is angular acceleration. So imagine this bar going around. It starts with some low velocity, and then as time goes by, tick, 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 it's going faster and faster and faster and speeding up. So that means omega is increasing as it's going. So there's a delta omega and over some time. So that means that's acceleration, the change in angular velocity per time. So average acceleration is alpha, with a little bar on top of it. And then similarly, the instantaneous angular acceleration is the time derivative of omega. So once you've got angular acceleration, there's something called tangential acceleration. So if this particle going around in a circle, it has angular acceleration alpha, then it has linear acceleration in meters per second squared of a sub t. Tangential is r times alpha. So if a whole object has some angular acceleration alpha, points on that object will have the same value of alpha, but their tangential acceleration will increase. It'll start 0 at the center and increase as you go upwards. And then don't forget that there's still centripetal acceleration. We've studied this before. Any particle that's just moving in a circular path will have centripetal acceleration, which is, I guess, r. Radial acceleration, same thing as centripetal, means it's going towards the center of the circle, and that's v squared over r. And you can work it out that in terms of angular velocity omega, it's omega squared times r. So now, the actual acceleration is along this diagonal. If you have an object that is both rotating and has angular acceleration, that means there will be tangential acceleration, so it's speeding up here, plus the radial acceleration. These are two components of the actual acceleration, which is neither towards the center of the circle nor tangent. It's along this diagonal. Okay, so when you have rotating objects, you can use those kinematics equations analogously to how we did linear kinematics. You apply the same equations, but just every time you see an x, you replace it with theta, the position, angular position. Every time you see v, you replace it with the angular velocity. Every time you see a acceleration, you replace it with the angular acceleration. So for example, here's our definition of average speed is 1/2 of the initial plus the final speed. Well, now the average angular velocity is 1/2 of the initial plus the final angular velocity. The final speed is the initial speed plus acceleration times time. Final angular velocity is the initial angular velocity plus alpha times time. There's your x equals initial position plus v times t plus 1/2 at squared. You get the same equation for something that's rotating. Final angular position is initial angular position plus the initial angular velocity times t plus 1/2 alpha t squared. And if you want to get the final velocity in terms of distance traveled, there's your linear equation. Your angular equation is, I guess, the final rotational or angular velocity is the initial squared is the initial angular velocity squared plus 2 times the angular acceleration times the change in angular position. Okay, so next section, 10.2, is on torque. Torque is the tendency of a force to cause rotation, and it depends on how big the force is, the direction in which the force acts, and the point at which it is applied on an object. And it's important if you're installing a spark plug on your car or tightening a bolt to a certain amount, you can use a torque wrench, which reads torque in foot-pounds. So the SI unit of torque is actually Newton meters, newtons times meters. The equation for torque is Rf sine theta, and as an example, we'll draw it on this meter stick. So you're holding it here, so there's sort of a pivot point there. This mass is pulling the meter stick downwards with some force F. There's some distance right there, R, from the pivot point. Okay, and the angle theta is actually the angle between R and F. So if you can continue going along R, and this is the angle theta right there. And so if here sine theta is about 90 degrees, so sine theta is 1, so it's just R times F is your torque. So the torque will be greater as you get longer R. And R times sine theta is sometimes called the lever arm. So here's a situation where you're trying to tighten a bolt, so you want it to turn counterclockwise like that. You apply a force in this direction. Here's your theta, would be right there. Your lever arm is this distance R, whoops, from here to here is called R. Sorry, from right there to the pivot, it's called R. R sine theta turns out to be right here. This is your lever arm. And that's less than the length of the handle because you're not pulling perpendicularly to the handle. If you want your lever arm to be the same as the length of the wrench, you pull perpendicularly. That's gonna maximize your lever arm, so it'll maximize your torque. And actually there is a way to get even more torque than that. You could increase your lever arm by putting a pipe on the end of your wrench, which extends this lever arm. And now if you pull perpendicularly, you can get even more torque on this bolt if you have a really, really sticky bolt. Okay, next section, 10.3, is on rotational inertia. So an object that's rotating about an axis, like this flywheel or something, tends to remain rotating about the same axis with the same angular velocity, omega, unless it's interfered with by some external influence like an external torque. Okay, so that's sort of like Newton's first law for rotation. Something that has angular velocity omega will tend to have constant angular omega unless acted upon by an external torque. So the property of an object to resist changes is called its rotational inertia. There's a symbol for that, I, rotational inertia, and the SI unit of rotational inertia is kilograms times meters squared. Rotational inertia depends on the mass of the object and also the distribution of mass around the axis of rotation. So for example, here's a dumbbell where the mass is close to where your hand is, where you're trying to rotate it. That's easy. If you put these masses further away from your hand, it becomes more difficult to twist that, and you can actually test that yourself. The greater the distance between an object's mass and concentration on the axis, the greater the rotational inertia. So it's like the rotational analog of mass. Here's another thing. Rotating this this baton around its axis is easy because all the mass is around the axis. If you turn it on its side and go around your head, it's harder to spin up. It's harder to give it angular acceleration. So here's a new equation. The net torque on an object, I should put a little net there, okay, is equal to the rotational inertia times alpha. So this looks like F net is equal to m times linear acceleration. So that's the linear analog for this equation. F is analogous to torque, m is analogous to rotational inertia, and a is analogous to alpha. Okay, so finding rotational inertia, it turns out the rotational inertia of a particle, a distance r away from the axis and a mass m, is m times r squared. If you have several particles like this, I don't know what it is, this thing that has m1, m2, m3, then you sum up over all the individual particles of m1 times r1 squared plus m2 times r2 squared plus m3 times r3 squared. Okay, so if you have continuous matter as opposed to a bunch of point particles, the rotational inertia is given by an integral. It's the integral over the whole volume of r squared times dm, where r is the distance of the mass element dm from the rotation axis. So this turns out to be easy if, for example, you have a thin ring or a hollow cylinder. All of these little dm's are at the same exact distance r from the rotation axis, as long as this is a very thin thin ring or a very, very thin cylinder. And so when you do the integral of r squared dm, the r is constant, so it comes out, and you just got the integral over all the volume of dm, which gives the total mass. So it's the total mass times this radius squared. If you have something where the dm's are all at different distances, then you have to actually perform the integral. So example 10.5 says find the rotational inertia of a uniform narrow rod of total mass m and length L about an axis through its center and perpendicular to the rod. So we can write down our equation for moment of inertia. It's the integral of r squared dm over the volume. Here r is going to be x, the distance from this axis. X will go from negative L over 2 up to positive L over 2. And we know that the ratio of this little dx to total length is going to be equal to the ratio of that little mass dm to the total mass. Rearranging that, you get dm is m over L times dx. So now we're ready to plug in. Integral from negative L over 2 to plus L over 2 of x squared times dm, which is m over L dx. We can now pull out the constant factor of m over L. Integral of x squared turns out to be x cubed over 3. We'll evaluate that from negative L over 2 to positive L over 2. So it's m over L times L over 2 cubed over 3 minus negative L over 2 cubed over 3. Remember, the cube of negative L over 2 is going to be negative L over 8, L cubed over 8. So the negatives cancel, you get a plus, and you get L cubed over 4 over 3, which is L cubed over 12. So mL cubed over L times 12 is 1/12 of mL squared. And that's exactly what it says in this table in your book, thin rod rotating about the center. So in all of these equations, it looks like you've got the total mass of the object times the length of the object or some size of the object squared, maybe it's the diameter or something, and then there's a factor out in front, a dimensionless ratio. So another one would be the thin rod rotated around its end. Again, that's ml squared, but now the factor out in front is a third. So a third's much greater than a 1/12 because much more of the mass now is further away from the axis when you rotate it around the end of the rod. We've got the disk, so we had hoop was mr squared. If you have a solid disk now where much more mass is towards the center, it's a half mr squared. solid sphere, you can do this integral. It turns out to be 2/5 of the total mass of the sphere times r squared. That's if this mass is totally filled. If it's a hollow spherical shell, like a ping pong ball, then it turns out to be 2/3 times mr squared, which is bigger than 2/5 because more of that mass, I guess, is kind of further away from the axis. Okay, so parallel axis theorem is saying that if we know the rotational inertia I sub cm about an axis that goes through the center of mass of a body, then the rotational inertia around an axis that's parallel to that is ICM plus m times d squared, where d is the distance from the center of mass axis to this new parallel axis, and m is the total mass of the object. So it looks like this. If you've got a sphere, a solid sphere, you know rotating at about its center is 2/5 mr squared. That's known from your table. What if you were asked what is the rotational inertia of a sphere rotated around its edge? Okay, so an axis right touching its edge. Well, now the distance of this axis from the old axis, d, is equal to capital R, so it's going to be 2/5 mr squared, that's the original rotational inertia, plus m times d squared, or m times r squared. So you've got 2/5 plus 1 is 7/5 mr squared. Okay, so rotational kinetic energy. If something's rotating, it has this rotational kinetic energy 1/2 I omega squared. I is the rotational inertia, which we discussed in the last video, and omega is the angular velocity, or angular speed. If you look at this big table, this is table 10.1 from your textbook. This lists a whole lot of linear equations from previously in the textbook, and now this new angular quantity or equation. So we had these before. Theta is angular position, omega is the angular velocity or angular speed, angular acceleration is alpha, rotational inertia I, torque is tau. Here's this equation for rotational kinetic energy. Looks a lot like the equation for translational kinetic energy, or linear kinetic energy from before. Instead of 1/2 mv squared, it's 1/2 I omega squared. And remember, here's this Newton's second law. Tau, the net force is equal to, or net torque is equal to the rotational inertia times the angular acceleration. Okay, and the work-kinetic energy theorem for rotation is that the change in an object's rotational kinetic energy is equal to the net work done on the object by the torques acting on it. And so by net work, what I mean is it's the integral of this net torque d theta over some angular range, theta 1 to theta 2. So it rotates by this delta theta, which is theta 2 minus theta 1. There's a torque applied to it the whole time. Well, it's going to change its rotational kinetic energy. So this is delta k rotational, which is the 1/2 I omega 2 squared, the final rotational kinetic energy, minus the initial rotational kinetic energy. Okay, so next up is called rolling without slipping. This is our last section. It's a bit tricky conceptually, so I'm going to describe it a couple of different ways. We'll start with this relative motion way, which basically means you've got two things happening. You have a wheel that's rotating around its axle, and then also the axle is moving linearly. So here's this rotation, which is now clockwise, omega, and that's a wheel, and it's moving towards the right. So the tangential speed of a point on the rim is going to be omega times r relative to the axle. But with rolling without slipping, the axle is moving at this speed v towards the right. And so this capital V is what we call the S prime frame. So we're going to look at this S prime frame, which is the axle frame of reference, and look at these 4 points. What's happening is that it's very simple. At each point, each point is moving at a tangential velocity, okay, which is omega times r, and it's going to be to the right at the top. On the right side, 2 is going to be moving down, 3 will be moving to the left, and 4 will be moving up. So now we're going to add this capital V to the right to all of these vectors, which is the speed of the S prime frame relative to the ground. So in the ground frame now, we've got the new velocity is V prime in the prime frame plus this capital V. So the point 1 at the top of the wheel, it'll be V1 plus V. They're both little v, and you get 2v, 2 omega r. In the S frame, the top point of the wheel moves at a speed 2v, where v is the speed of the axle. If you look at point 2 on the right side of the wheel, you're now adding two vectors that are perpendicular. The rotational part, which is going down, and then the axle part, which is going to the right, and you get square root 2 times v as being the length of this vector. So in the ground frame, the point on the wheel just on the front there is moving diagonal down and to the right. Point 3, at the bottom of the wheel, what you've got is the rotational velocity component going to the right and the axial component going to the left, and those cancel out. V minus V is 0. So in the S frame, the ground, the bottom point is at rest. So that's the idea, is that in the axial frame it's going all around. In the ground frame, the top is moving at twice the axial speed. Every other point is kind of at some intermediate speed, and the bottom point is at 0. And you can think of the whole wheel as rotating about a pivot point, which is at the bottom. And so this here, so just to sum up, the wheel rotates with angular speed omega. The axle moves with linear speed omega times r, where r is the radius of the wheel. And since the bottom point is always at rest, it's static friction which acts between the ground and the wheel. It's one of the important things here. And another way to look at it is that instead of thinking about a circle, let's think about a triangle that has 3 sides. If you imagine it rotating, well, this bottom pivot point does not move. That's a fixed point. What if you had 4 sides? Rotate it. Again, the pivot point does not move. What if you had 8 sides? Rotate it. Again, the pivot point does not move. So, etc., etc. If you had an infinite number of sides, which would just be look just like a circle to our eyes, you still would not expect the bottom pivot point to move. I don't know if that helps, but it's another way to look at it. So it might seem hard to believe, and if you look at my bike tires as going along, you might think that it's sliding as it's going. But let's actually go a little further and look. Let's look at my back wheel, which is flat. And now you can see pretty clearly the rubber is getting laid down at the front and picked up at the back, but when it's in contact with the ground, it's not actually sliding along, okay? And even if the tire is pumped up, it's still true that you're laying down rubber at the front, picking it up at the back, but it's not sliding along at the very, very bottom. Okay, so the rolling without slipping constraint is an equation. There's actually 3 equations, but the textbook really dwells on one of them. So the center of mass motion of this axle, okay, is delta x is equal to delta theta, how much the wheel rotates, times r, the radius of the wheel. Here's the equation the textbook really likes, which is that the speed of the center of mass of the wheel equals omega times r. But both of these are true. And then also it's true that the acceleration of the wheel is going to be the angular acceleration of the rotation times r. So these are all constraints, but this is the one that you see most often in problems.